right, so let's talk about Dockerfile syntax. In this section, I'm going to give you kind of a full list of all the Dockerfile commands, well, almost all of them. Now, to be clear, the goal is not for everyone to be able to remember all these Dockerfile commands. The goal is more to know that these things exist. So that if someday you need something like that, you might remember, oh, I think there was something along these lines. So it's, you don't have to remember all these. It's more like to give you an idea of what exists and what's available. So there are many commands that we have seen already and many principles that we have talked about. So for instance, the first instruction should be from. So you need a from line. You can't just start with run or cmd. You need to put from in the beginning. You can have comments, like if you have a line starting with hash, it's going to be a comment. So, okay, we talked about run already. We talked about, expose. I don't think we formally talked about expose. I mean, I kind of mentioned it briefly, but it's a good idea to have that here. When you do a docker run dash uppercase p, like like we did yesterday with the Nginx image, Docker will publish that port. How does Docker know which port to publish? Because there is an expose command in the Docker file. That's how. So you can have multiple expose commands if you want. You can expose multiple ports. You can expose TCP and or UDP ports. That's it. Copy. Okay, we talked about copy. I think I talked briefly about add. Add has some kind of extra superpowers because it can automatically download files. It can also automatically unpack zip files and tar files. I don't recommend to use add. If you really need to do that, I would suggest that you use multi-stage builds instead, and we will talk about that very shortly. So add, it's here for legacy reasons, but personally, I would stay away from it. Volume, that's how you declare a particular directory to be a volume. Remember, earlier today, I was talking about how remember that little metaphor when you have your container and you have some data in the container, and Compose knows, oh, this is the data, and so when you update the container, it's kind of reattaching the data to the new container. And how does it know where the data is located? Thanks to that volume instruction, basically. So when you say volume valid MySQL, it means the data is going to be stored in that directory. Workdir, that lets us change the directory. Env to set and run variables. User, okay, that lets us change the user, so like the Unix user running in the container. By default, the user in a container is root, and you might want to change that. Tomorrow, when we get into the advanced topics, I will talk a little bit about security and we'll go back to that. But long story short, it's usually a good idea when you run a container to not run as root. Now, I'm using kind of weak language here. I'm not telling you, oh, you should absolutely run things with a different user because it's better. No, it's a little bit more subtle than that, because yes, in theory, running as non-root gives you more security, but sometimes it's also a lot of extra trouble and lots of extra difficulties, and depending on the container engine that you use, it might not get you any extra security. So, variable, it's maybe it's a little bit like if someone tells you, oh, you should absolutely lock your door or something like that. Yeah, there are some scenarios, some places where you probably want to lock your door for security, but there are some other places where locking your door, you know, sure, in theory that's better, but there are some scenarios where that doesn't really change anything, so why do it? CMD, okay, we talked about CMD, we talked about entry point, so we can skip these ones. And now at the end, I have half a dozen of, I would say, more exotic Dockerfile commands. Let's see in which order we're going to talk about them. Let's start from the bottom. Shell. Shell is used to change the shell in the container. What's that? Well, the shell is the thing that we use when you don't use the JSON syntax. Okay, maybe if I show you a little reminder. Remember, like we were saying, you have bin-sh-c all the time. That's the shell. So if you want, you can change that. What's the point? Well, if you are on Linux containers, if you want to be really fancy, you could decide, oh, you know, I really like ZSH, for instance, or fish or whatever, and I want to use that in my Docker files. Then you could use shell to change the shell. But the real use case is for Windows containers, because on Unix, so Linux, macOS, etc., all the shells are pretty similar. So changing from one shell to another, it's not really a game-changing decision. However, on Windows, you have the classic kind of old shell, so cmd.exe, and then you have PowerShell, which is completely different. Significantly better and improved, and etc., etc. And so that's when you might want to change, like, from one shell to another, because they have completely, like, radically different ways of operating. But honestly, on Linux, I don't remember if I ever used that shell instruction a single time. I'm not saying that you will never need it. Again, I'm just mentioning that because if someday you're like, oh, I wish I could change the shell, bingo, you can do it, but there is a good chance that you will never need to. Health check, that one is, that's a little bit sad in a way. So health check lets you define a way to check that the container runs properly. This is pretty much only useful if you run Swarm, like the Swarm orchestrator. And nowadays, almost nobody does that. Almost everyone using an orchestrator uses Kubernetes. And on Kubernetes, we don't use that health check. We use something else instead. Why does Kubernetes use a different health check? Without diving into too much details, but because on Kubernetes you have multiple kinds of health checks depending on the situation, and so the Docker health check is just not good enough. You know, it's with the Docker health check you can have only one health check, and on Kubernetes we need to have liveness probes and readiness probes, and so it just doesn't match very well. So once again, health check, we can ignore it. Stop signal. Okay, that one I think I might have used it once. Stop signal, this is to change the signal used by Docker stop. I think it's used in some official images when you have a server that doesn't stop with sigterm but with another signal. You can use that to configure which signal to use. Okay, now let's get to something a little bit more interesting, arg. Arg, like argument. This is a little bit like env, but with a big difference. When you set an environment variable, it's going to be visible in the final image, but if you set an argument, it will not. Okay, little demo. Arg demo, we go there and I write a Docker file from Ubuntu. And I'm going to put like, and let's say database password equals secret sesame hello, and arg API key equal hello 1 2 3 4. Okay, let's look at that. So docker build dot dash t arg demo. Now I get into there, and if I look at the environment, in the environment I have the database password, but I don't have the other one, the API token. However, if I, in my build process, I could use both. Like for instance, I could say run echo curl, I don't know, my api.whatever.com, I don't know, dash h x of header API key, something like this. So you can see here that it did it did replace $API key with the value of that argument, but that argument doesn't end up being in the final image. So arg is a way to have a build parameter. Another really convenient thing is that you can do dash dash build arg API key equal very secure. So you can override that. And so now you can see that it did replace API key with very secure. So long story short, arg is a little bit like env, except that the variables that you define are only available during the build. They don't show up in the final image, and you can override them during the build process. Use cases include passing keys and credentials and things like that that you need at build time, for instance, to download dependencies from private repos and things like that, or setting some build variable, like the version number of this thing or that thing or whatever that you want to pass at build time. Then we have label. So label lets you add arbitrary labels to your image. So that's purely decorative. It's a little bit like an environment variable, except it is not visible inside the container, but it's visible outside the container if you do a Docker inspect. And finally, on build. Okay, on build is really complicated. Well, I think we're not supposed to say it's very complicated, because then we're kind of setting ourselves up for failure, like, oh, this is complicated, so our brains are like, oh. But on build is honestly a little bit complicated. What on build does is that it's going to set aside some commands to execute them later. So if I build demo, oops, sorry, and I need to have like a first image and second image. Okay, so in first image, I do from Ubuntu, and I'm going to do on build run apt-get update. Now I docker build first image. Okay, that's it. Now I go to second image and I do from first image run apt-get install Figlet. And now I docker build dot dash t second image. And now it's going to run apt-get update. So I don't see what happened here, but in my first image, right? First image, I put the on build, which means set that aside for later. Don't execute it now, but execute it whenever we build something on top of that. And so when I build my second image, we do from first image, and at that point, it's as if automatically we had inserted all these commands right there between the from and the run. What's the use case here? The idea is to help you to factor some Docker files, like ideally, if you work on lots of applications, so let's say, you could be, again, the example of the web agency, but you could also be a big financial institution like bank or whatever, and you could have hundreds, if not thousands of applications. And when you take a step back and you look at your applications, you might notice, hey, we have 200 Python apps, and the Docker files are almost always the same stuff. You pip install requirements.txt. When we have Node applications, it's npm install. So all these Docker files are very, very similar. I wonder if we could kind of factor that a little bit. OnBuild can help you with that. To be honest, I haven't seen many folks use it in the field, maybe because it's kind of complicated and weird, but it's there just in case one day you need something like this. All right. Do we have any questions before I move on to multi-stage builds, because that's going to be the last big chunk for today? Good question. Should OnBuild be repeated to add more instructions? Yes. If you put multiple OnBuild, then you will kind of stack multiple instructions to execute. Yep. All right. Let's talk about image optimization. And first, why would we even want to reduce the size of the images? Well, first example, I don't know if you remember from day one, where is, myC image. So this is a 391 megabytes image, pretty big. And if I do a Docker history and I look a little bit more closely, my hello program is 16 kilobytes, but my image is 300 megabytes. So that's 20,000 times bigger. Like, what's going on here? Like, there's that sounds like there is a problem. So I have my base Ubuntu image, which is 77 megs, the list of packages 40 megs, the compiler 273 megs, and intuitively, when you compile something, you don't need to keep the compiler in the final image. So I feel like we can do better here. And my first idea would be, well, after building, maybe we could just remove the compiler because we don't need it anymore. The problem is that it's not as easy as it seems. Like, for instance, if imagine I build my Hello World program and then I remove a bunch of files, remove the compiler, etc. That doesn't help, because yes, the compiler and all these files will not be in the container at the end, but they will still be in the layers. Like, if I have something like this, like you install a bunch of packages and then later you run apt-get remove, that doesn't work, because when you download the image, you need to download all these layers. So you end up downloading these files, even if you remove them later down the line. That's exactly the example I was giving you earlier. When you have a Git repo and you add an image and then you remove the image, if you git clone or git pull, you still get that image because it is in the history of your Git repo. Okay, so we can't do that. That doesn't work. Next option, we could do something like this. This is called like collapsing layers. So when you have multiple instructions, you just put everything in one layer. So apt-get update, apt-get install, compile, and then apt-get remove. It works, but this completely ruins the cache. If you do that, then each time you change your hello program, it's going to redo the whole thing, re-download the compiler, compile, etc. So yes, you end up with a smaller image, but at the price of much longer build times. So that's also not a good solution. Another solution would be, well, what if we could compile locally? I compile on my machine and then I copy the binary to the container. It kind of works, but there are two problems with that. The first problem is that if you are not on Linux, then you need what we call a cross compiler, because the container is a Linux container. So if I'm on Windows, I need to compile a Linux program. And it's not impossible. In fact, it's perfectly doable. But depending on the language, that can be really annoying. If it's C, super annoying. If it's a relatively recent version of Go or Rust, very easy. And if it's something else big, it depends. So compiling locally, not so great. Another issue is that if you compile locally, you kind of lose the whole point of containers, which is to have something that works everywhere. Because now you say, oh, to build this image, you need to install Go or whatever locally. No, I don't want to install stuff locally. I want stuff to be in the container. So again, not a good solution. There is a -- squash option, which can help a little bit, but has other performance issues, etc. So also not a good solution. All right, I just listed a bunch of not so good solutions. So what is the good option then? It's multi-stage builds. All right, let's see how these multi-stage builds work in practice. So the idea of a multi-stage build is that you have, at the minimum, you have a build stage and a run stage. So in the build stage, you're going to build or compile the program. And then in the run stage, you just get the compiled program and put it there. Concrete example, how do we do that? So I get my hello world in C. So how does that work? Whoops, why do I have all that stuff here? Interesting. I don't think I meant to have all that. And I can remove this. Okay, I think that's what we had. So docker build the .-t hello. All right, okay, so that's my first iteration. That's my first version of the image. That's make hello world. So I have this 16 kilobytes binary here, but it's a really big image and I want to do better. How do I do that with a multi-stage build? So what I do is that I find the location where we built the program. And that's here. That's when we compile hello.c. And here I'm going to start a new stage. How do I do that? I do from, and here I'm going to put from Ubuntu. That's my new stage. Now copy -- from, and I'm going to put 0. So that's stage 0 and that's stage 1. And if I have multiple froms, you could have from 1, 2, 3, 4, etc. So copy from 0 /app/hello in the current directory. So I'm basically getting the compiled program from there and getting it in there. All right, let's see that in action. So docker build -t, I'm going to call that hello multi. And now I can do docker run hello multi. It says hello world. And if I look at the size of that image, great, it's only 77 megabytes. So we went from 390 down to 77. So we kind of divided by 5. This is a 80% size reduction. Nice. Now, if I look closer, history, hello, multi, I'm like, okay, cool. You only have your 16 kilobytes program, but that's still in a 77 megabytes image. So I think we can do better. Okay, before we do better, there was a pretty good question about can we alias our stages? And yes, we absolutely can. When you do your from here, you can do from Ubuntu as build, and then here I can do copy -- from equal build, and that's exactly the same thing. And so typically, if I just have 2 stages, I don't bother putting aliases. But if I have more stages, then yes, absolutely, I will put aliases because it becomes a nightmare to keep track of which is which. All right, how can we do better? Well, I mentioned a few times already since the beginning of the course that we had Scratch images. We have a special image called Scratch. And here I can do from Scratch. So Scratch is not a real image. Scratch is a completely empty image. There is no file, there is nothing in it. So when you do from scratch, it means start from nothing. Because in English, when we say doing something from scratch, it means you do it like from the most basic ingredients. So cooking from scratch, it's like you make the dough and everything yourself. So from scratch, it means we start with a completely empty image. All right, let's try this. So I docker build. I'm going to call that one hello scratch. How big it is? Nice, 16 kilobytes. That's a really small image. Yay. Now there is just one tiny little problem. That image doesn't work. Okay, let's look at that error message. It says binsh no such file or directory. That's kind of interesting and weird because in my Docker file, I'm not using binsh. It's a cmd./hello. So why do we have binsh? Maybe you guess, maybe you remember, but basically, since I'm using the string syntax here, I have /hello, but what Docker does is actually sh-c./hello. And so what should we do? Yep, indeed, we should use the JSON syntax. All right, let's go back to the Docker file. Let's use the JSON syntax. Let's build it. And let's try to run it. And now we get an even worse error message. It says just like no such file or directory. I'm like, what are you talking about? Which file are you not finding? Maybe I've put like the wrong thing here. Maybe it's not /hello, what's going on? Now the problem is that if I try to get the shell, hello scratch. If I try to get the shell here, that doesn't work because I have a scratch image. I have a completely empty image, so I can't even have a shell. That's kind of the problem. If you use a scratch image, you have no tooling, no nothing. What do we do here? Well, no pun intended, but we scratch our head trying to understand what's going on. So that's a good opportunity to check questions. So yes, indeed, what the idea of multi-stage is to try to get rid of the layers that we don't need, except, so the high level idea is this. Yeah, we try to get rid of the layers that we don't want, except I think I would want to think about it the other way around. it's not that I want to get rid of the layers that I don't want. It's more like I want to keep only the bits that I really need. I don't know if you see the difference. Instead of thinking in, how would I say, subtractive logic, it's not like I want to remove this. No, it's kind of the other way around. I start with nothing and I add only the things I need. But at the end of the day, yes, it's the same idea. All right, so what's going on? What should we do here? Well, first, can I go and have a look in that container? That's tricky because, well, I know the container is not running, so I can't even do a Docker exec. Well, what I can do, that's going to be a kind of semi-advanced technique here. Look at this. I'm going to do a docker create -ti hello scratch /busybox sh. So I want to run that Scratch container, but I want to run a shell. And indeed, I'm going to CP a tool. But it's kind of weird to do that because you're like, wait a minute, you're creating a container and you want to run a shell with BusyBox, but you don't have BusyBox. Yep, but hold up. Now we're going to docker cp bin BusyBox in C7544 /BusyBox. Whoops. Yeah, BusyBox. Okay. And now I can do docker start C7544, and now I can do docker attach C7544, and here we are in the container. So this might seem very counterintuitive because at first I would think, oh, I want to start the container and then I want to copy the tool and then I want to exec, but no, we can't do that because if we run the container, it fails to start. So here I am kind of starting the container with BusyBox, and because of the sequence of operations, it feels a little bit weird. I create the container telling it, yes, you will run BusyBox, and then I copy BusyBox and then I start it. All right, so here we are. As you can see, we don't have a lot of things in there. We have a very bare bones /dev. We have a very bare bones /etc. We have a /proc. We have a /sys. And I have indeed my hello program. So I'm like, okay, let's run the program. ./hello, not found. Like, what? That's kind of weird, right? The program is here, so why is it telling me not found? Well, maybe the cat has some ideas. No, nothing, no input from the cat. Okay, so what's going on? To understand what's going on, I'm going to go back to the first iteration in my, whoops, sorry, hello, yep, there we are. Because here it works, no problem. And I'm going to use, okay, file, so sudo apt-get install file. Oh, sorry, just apt-get install. I don't need sudo, my bad. File, what is file? File is something to guess the type of a file. But it's not just, like you could do that by looking at the extension. Like if you are, let's say, if I'm here, I have a bunch of screenshots that I took. So these are PNG files. So I don't need to be a big expert to be like, oh yes, this is an image, yes. If I do a file on that thing, it's going to tell me, yep, it's a PNG. That's the resolution. But I could say, oh, you're cheating because the resolution is in the file name. Okay, well now, if I take that image and I just call it what? If I do file what, it will still guess that this is a PNG image, this is the resolution, this is the type of color, etc., etc. So file is going to do some pretty good in-depth analysis on a file. That's why it's called file. So if I do file hello, this is telling me it's ELF, so that's executable Linux format, 64-bit, PIE, that's for program independent execution. It's not important. This means Intel architecture, blah, blah, blah. Dynamically linked interpreter /lib64 LD-Linux, blah, blah, blah. Well, this is a file that exists here. /lib64 LD-Linux, blah, blah, blah. And obviously that does not exist in my other Scratch container. Where is my other container? I stopped it because I am attach. There we go. Of course, /lib64 LD-Linux, blah, 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 that does not exist there. So that's the file that is not found. Okay, so what is this about? What is this LD-Linux? So, tiny little bit of computer history, etc. In the days of the first computers, when you have a program, this is actually just a bunch of memory, and the computer is kind of reading the instructions from that memory. So imagine you have like a recipe, well, a set of instructions, and you load that in the computer, and the computer follows that. So that means that before you can run the program, you load it into memory because the computer only executes from memory. Okay, so what? So for a while, when you wanted to execute something on the computer, you would load it in the memory and that's it. But then we started to introduce computers that were able of multitasking, well, running multiple programs at the same time. And we realized, oh, we have a lot of duplicates in there. Like when you write programs in C, almost all the programs that we write are going to use printf and malloc and fopen and strlen, etc., etc. There is a lot of functions that we use all the time, and that's called the standard C library. So some folks started to think, would there be a way that we don't duplicate that in every single program that we install on the machine? And so they started to think about this concept of shared library. So on Linux systems, these are SO files. Like when you see a SO, this stands for shared object. On Windows, you will see DLL, which is for dynamically linked library, I think. On macOS, it's dylib for dynamic library, etc. Same idea. This is a bunch of code that is shared between multiple programs. All right, so what? Well, so now what happens is that you have your program, for instance, your hello world here. And when you want to run that program, you actually need to link it, to put it together with the library. Okay, what library do we need for that program when I can use LDD? LDD is going to tell me more. LDD is telling me, yep, if you want to run that program, you need this and that and that. The problem is that these files don't exist in my Scratch containers. Like, these files are kind of essential libraries, very important files, and they are not in the Scratch container, so my program doesn't work. All right, what's the solution? Well, one solution would be to copy these files in my Scratch container. That's not so great because it would be a very manual process. Like, this particular program only uses these libraries, but for instance, if I look at binbash, bash is using also libtinfo, whatever that is. If I look at, I don't know, bin/top, oh, bin/top is using all these fascinating libraries. So that kind of getting a little bit annoying because I would need to find a way to list them and copy them in the images. No, I don't like that. The other option is to tell to our compiler, to the C compiler, hey, why don't you give me a static executable? Why don't you get all these libraries and instead of having them like separate from the program, put them together with the program, give me a program that is standalone and doesn't need all these extra things. And how do we do that? Very easy, we just add -static. All right, so we try again, Docker build, I'm going to call that one hello static. Now the big question is, does it work? And yes, it does, so that's pretty great. Now, what's the size of that image? 900 kilobytes. So now you see we're kind of in the middle. It's much smaller than the 77 megabytes that we had. So, you know, like if I reduced the size by what, 98.5% or something like that. So that's great optimization. But it's still bigger than 16 kilobytes. Yes, because 16 kilobytes, that was my little program, but missing all these important libraries. And with 900 kilobytes, now I have the important libraries. Okay, so here I could think, well, let's stop here. You know, we have a really small image, that's great. No, I don't want to stop here because this image is still a huge pain in the neck to operate. You know, if I try to get a shell, remember, no, that doesn't work. I can do that. So can I have an image that is both small and also easy to operate? Yes, we can. And what we're gonna do is multiple steps. First, BusyBox, next, Alpine, and next I'm going to tell you that this will all for nothing. Okay, first step, BusyBox. What I can do instead of from scratch, I do from BusyBox. That's it. Build hello BusyBox. And now if I Docker run hello BusyBox, it works. But if I do Docker run -ti hello BusyBox sh, I get a shell and I have my hello program here, but I also have all the tools of BusyBox, and my image is very small, you know, 2 megabytes. That's pretty nice. Sure, it's like twice bigger as 900, but it's still super small compared to that. Okay, so that's level 1. Now, what if I, you know, like I'm running this and I'm like, oh, I really would like to have curl, for instance. Well, that's a BusyBox image, so good luck installing curl. But what I could do is use Alpine instead. Okay, so I docker build -t hello Alpine. How am I going to call that? Alpine multi1. So this is 8 megabytes, so still a little bit bigger, but I can get a shell here. I have my hello program, and if I want curl, I can easily install it with apk-add. So that's also a really good compromise. Now, this was all for nothing. Why? I'm going to try and explain. If my goal is to get the smallest image, then yeah, you know, it's great to use these techniques. Now, if I look again at the layers, so Docker history, hello multi, that's the layers specific to my image. That's where I have my hello program. These layers here, yes, they are 77 megabytes, but these are the Ubuntu layers. So if I have multiple containers using Ubuntu, they are going to reuse these layers. So if I talk about let's say the cost of that image, if I just pull that image and just that image and nothing else, yes, the cost is 77, 78 megabytes. But if I pull that image and other images using Ubuntu, or if I update that image with a new version of the program, the cost is not 77 megabytes each time, it's 1 times 77, and then you add the cost of that layer, which is very small, like 16 kilobytes. So you see, like if I try to compute the cost, instead of being a fixed thing, it's a kind of formula when there is a one-time cost and then there is a small cost each time. And the small cost each time, that's where it's the lowest because it's 16 kilobytes. So yes, if I want to deploy only once and I want to deploy, let's say maybe like on a Raspberry Pi or a really small embedded platform, or I want to deploy to my watch or to a really small platform, then yes, maybe I want to use a static build so that it's really, really small. But if I want to deploy on servers where I'm cool with downloading 77 megabytes the first time, but then I want each deployment to be really fast, that's going to be the most efficient option. So that's really interesting because that's not very intuitive. If I show you these techniques, you might think, oh yeah, this seems to be the best option and we're going to use that. But no, it turns out that very often the best option is actually that one. So that's the first multi-stage build that I was showing you. The big takeaway of this is that if you're thinking about optimizing your images for size, very often the single and best thing you can do is multi-stage. You don't even need to think about static builds and Scratch and Alpine and BusyBox, etc. Just a multi-stage, very often, that's what will give you the best results. Now, question, if we use BusyBox or Alpine, do we still need static? Excellent question, and let's give it a try. So let's remove static, let's use Alpine, and let's build, and I'm going to call that Alpine Multi-2. Now Docker run, and that doesn't work. I'm like, that's strange. Let's go and have a look. So I have my hello program, and it says hello not found. So I'm going to install file and do file hello, and it say, yep, you're looking for /lib64/ld linux blah blah blah. And if I look at, nope, I don't have lib64. However, what I have is /lib, and instead of having ld linux blah blah blah, I have ld musl blah blah blah. What's going on here? Well, and I think if I try this, it's that works, but that's kind of a hack. So what's happening here, the reason why if I take the Ubuntu program and I put it in Alpine and it doesn't work, that's because Ubuntu and Alpine use different system libraries. In fact, this is one of the like the secret sauce or the technique that Alpine is using to be so small is that it's using a different system library called MUSL or musl. And so when you take a program built for Ubuntu or Debian or CentOS or RHEL or etc., and you try to run it on Alpine, it doesn't work. Except if it's a static program, because the static program has no dependency on these libraries, and then you're fine. If it's the first time that you hear about these static libraries, dynamic libraries, etc., don't panic. Don't worry too much about it. I think it's it's useful to know about this. If you are building and compiling like C code and things like that, then yeah. But if you're working with Python, Node, etc., there is a good chance that you will never have to worry about that. So don't panic. Can I show again the multi-image? Yes, absolutely. There we go. And wait, that one doesn't work, so I'm going to give you one that actually works. Voilà. So that's a Docker file that works. Now, in the last, 5-10 minutes that we have, I'm going to show you a couple of other techniques if we are still trying to do like smaller, and exactly, excellent question, and that's exactly what I wanted to show you. Is it possible to use Alpine images for both build and run? Yes, and that's exactly what I was about to show you. So here, let's go with from Alpine. Now, if I'm on Alpine, I don't have apt-get. Instead, I have apk. And so to install the C compiler, I do apk add build base, if I remember well. And everything else is pretty much the same. Okay, let's try this. So I'm going to call that Alpine Multi 3. And now if I do docker run hello Alpine Multi 3, it works, so that's great. And if I look at the size of the image, it's 7 megs, so that's pretty nice. Another thing that you can do, again, if you're in the, if you're trying to get like really small images, we can actually get a static binary with Alpine. And here I would do from scratch. And now I would call that like Alpine scratch, let's say. And this works. And that image is 74 kilobytes. Because the Alpine library, like I was telling you earlier, is much smaller than the standard, the other one. The other one is called the glibc or the GNU libc. That's the standard C library that we use on every other Linux system, basically. All right, so what else can we do? Well, that's really the main two things if you want to optimize image size. First, using multi-stage. Like first thing we should do, multi-stage. The second thing that we can do, we don't have to, but we can, is see if we could switch to Alpine, because very often Alpine images will be much smaller. So for instance, if I go to the Docker Coins app I was showing you earlier, and I look at these Docker files, you can see here that it's using from Ruby Alpine. Sorry, the Walker, which is in Python, also from Python Alpine. So it won't work every single time. There are sometimes there's going to be a small incompatibility or whatever, but when it works, it's going to give you much smaller images. Also useful to know, especially if you do like data science, machine learning, etc. Unfortunately, if you try to use Python Alpine and then you install machine learning packages like PyTorch or NumPy, etc., or it might be counterintuitive. You might end up with very slow build processes and very big images. Why? Because if you use Python and you install, let's say, NumPy, if you are on a glibc system, it's going to download a pre-compiled version of NumPy, so this is really fast. If you are on Alpine, there may not be a pre-compiled version of NumPy, and so it will have to rebuild it. So it's a kind of counterintuitive result here. I mean, what I want you to remember is not necessarily, oh, if you do data science, then you should be careful because this or that. It's more like, there are some scenarios where using Alpine won't improve things. So my recommendation is, first try multi-stage. I think I cannot emphasize that enough. Try multi-stage because that's what's going to give you the best results. And then if you want to go even farther, you can try Alpine and see if it works for you. Maybe it does, and maybe it gives you better results. Maybe it doesn't work, and then you just stick to your simple multi-stage build. If you want to know more about optimizing, like to have really small images, I have a whole repo called MinImages. Nope, singular, I think, it's MinImage. I'm going to put the link in the chat. And that repo has a ton of examples in C, Go, Java, Python, Rust. Very simple code each time, like hello world level. And each time we have a bunch of different Docker files, and we try to see like how we can optimize, how we can make things better. And that repo comes along with a series of 3 blog posts available in both English and French if you want to explore these topics. Right. What else did I want to say about that? Oh yeah, something, like, why is it important to optimize for image size? Well, there are some scenarios where the contrast is really huge. Like you can see here, 300 megabytes, and after optimization, like we divide by 5 or by 10 or by 100 the size of the image. So yes, okay, but why is this important? Well, it's important to reduce the time it takes to build and to push and to pull the images. Now, is that important? It depends. And I'm going to kind of wrap up with this. When you're trying to optimize something, it's always important to do profiling. So, when you run a program and it's slow, the smart thing to do is not to dive in and try to optimize things. No, the smart thing to do is to profile. If that program takes 5 minutes, where are these 5 minutes spent? Like maybe I have some code to rotate an image and it takes 5 minutes. What is taking time? Is it loading the image, rotating the image, saving the image? Maybe I will try to optimize my rotation algorithm with like matrix and GPU and whatever, only to realize, oh no, that's because I'm using a really fancy compression format, and so my program takes 5 minutes and 59 seconds to save the image because it's using like wavelet compressions or whatever. So in that case, optimizing my rotation algorithm is completely useless. So step 1, profiling. In the land of containers, profiling means that if I have, let's say I have a really slow deployment process, like I commit my code, push, and then it takes 3 hours before my code is in production, I want to know what's happening during these 3 hours. Maybe yes, in these 3 hours, there are 2 hours spent pushing and pulling images. Then in that case, maybe I want to optimize the size of the images. Now, maybe what happens is that instead of starting the build right away, there is a cron tab that only builds every 3 hours. So that's why it takes 3 hours. But if I set up a webhook to immediately trigger the build, maybe it's going to be faster. Or maybe the problem is completely different. Maybe I have some CI/CD workers and it takes 3 hours before one CI/CD worker is available because there is a really long queue of build jobs. And so in that case, maybe I want more workers or dedicated workers or something like that. So what I want to say is that, yes, I showed you some techniques to optimize Docker files, and it's great and it's fun, but the important bit is, before applying these techniques, make sure that this is really the problem that you have. Make sure that the image size is really something that you want to optimize for. All right, that's it. So if you want to practice all that, you can try as an exercise to optimize the Docker files for Wordsmith by using these techniques. So at the very least, you can use multi-stage. And if you want, if you want to go farther and want to optimize things, you can try to use Alpine or even look for other solutions to try and get the smallest image possible. And tomorrow I will show you how to do that, so how to optimize the Docker files. So what's left for tomorrow? Yes, good question. So tomorrow, of course, we're going to spend a little bit of time to optimize these existing Docker files. And then we have advanced topics. So tomorrow, we're going to talk about BuildKit, multi-architecture platform builds. We're going to talk about network drivers, the building blocks of containers, and I will also give a short introduction to orchestration. So tomorrow it's mostly advanced topics. So, it's, I would say, if this week was your first big exposure to containers, for tomorrow, I recommend that you just, sit back, relax, and listen to the stuff I'm gonna say, but it's going to be less important for you. Tomorrow, it's going to be maybe interesting for folks who already had a little bit of Docker experience and want to, get their black belt in Docker or something like that with all that advanced content. All right. Thanks, everyone. I wish you a good afternoon, evening, or night, depending on your local time. And see you tomorrow for the fourth and final day of training. Thank you.